Speakers, as minimum, stealing your thunder, quite possibly taking away most of your presentation. So I'm sort of feeling that I could say, what they said and just sit down. Maybe I could add a little bit of a perspective of someone who's got their head down a lot, trying to avoid the alligators and not looking up too much, thinking that I'm trying to drain the swamp. There we go. So last summer, focused some attention on high-rise condos, high-rise buildings in general, but driving from the issue of breaking balcony glass. The glass, in my mind, or the issue of the breaking glass, is more of a bit of a case study in how the media controls some aspects of events. Misinformation, some of it unfortunately coming from engineers. Policy or code requirements that are at least out of date, if not in some cases almost incorrect. And then remedial measures taken to adjust policy that may not have worked as best as they could have. As was mentioned, I've been fairly intimate with this issue of the breaking balcony glass. We were the investigating engineers on 3 of the 4 buildings that were in the news and a few others that didn't make the news. What we hear from the media is that the breaking glass was caused by a long list of potential things. We had bird strikes, we had high winds, we had hot summer temperature, we had the fact the glass wasn't made in Canada, so therefore it breaks. We had unscrupulous developers that maybe scrimped on very thin glass or something like this. As part of our investigations, we looked at hundreds, if not thousands, of pieces of glass coming off of these buildings. Every single piece we looked at was completely code compliant. We couldn't find anything wrong with the glass other than it broke. That's the key, is that other than it broke. I got 3 lines later I was supposed to say that. But so it's not only these guys are stealing my thunder, this guy is too. The audience is against you. So we look at the causes. I said there's not all those causes. The primary cause wasn't a contaminant within the glass. It's commonly referred to as nickel sulfide, very small particles. Now, these particles are allowed to be in the glass. It's very specific within the codes and standards. There's certain sizes and distributions that allow this to happen. So what we have is a situation where, in the case of the developer, for instance, he's hired a reputable firm to install his balcony railings. He's hired professionals, architects and engineers, to review the work of those firms. He's hired third-party review to be done on site while the railings are installed and have them tested. The railings are sampled by city inspectors and so on. So basically, the developer did everything that he was supposed to do. He followed the in-place policies, but the glass still broke. So then we go from that to the fact that when I've got to address the issue, and maybe we address it through a policy change. In this case, it's an emergency amendment to the building code. So a panel is formed with a variety of stakeholders, unfortunately with different vested interests, at least in my mind. I was involved in this panel, and it was a very educating and frustrating process for me. To me, it was black and white. There's the physics involved, there's the structural strength of materials and so on, and you can come very quickly to what I thought were relatively easy answers. But when you put in a mix of a variety of different people from all different areas, different stakeholders, at least in my view, you come out sometimes with solutions that are not representing good science or good engineering. Everybody's going to see in the very near future what the results of this panel, the conclusions they came to. In my mind, I don't fully endorse those solutions, but that's the result of the policy development process. Tim and John did show some buildings, so now I get to do the same thing. A couple of buildings that have been noted on. One is First Canadian Place, which you notice sort of in the center there. Very prominent Toronto building. That picture was taken very early in a redefining first was the process it was called. And this building has been pointed to in the media as an example of what condo owners are to look forward to, that they have to strip off their exterior walls every number of years and replace it with a new wall system. What was actually done on this building was an awful lot less than that. It was undoubtedly a very significant undertaking, but you had the process of removing white Carrara marble, which, while it's very durable in Rome, is not very durable in Toronto. particularly when it's used in a thin cut mode on a high-rise building. So you're removing an outer cladding element. You're not taking the whole wall off, and you're replacing it with a glass element, which in the Toronto environment has proven to be a very durable material. Talking about this building from a thermal or an energy perspective, there are people that point to it and say, oh, it's again, a high-rise tower, not very thermally efficient, and so on. Of the downtown towers, this is one of the most efficient in terms of the exterior wall. At each floor slab level, there's about a 7-foot deep steel spandrel beam that wraps that floor. The whole outside surface of that beam is insulated with 3 to 4 inches of mineral wool insulation. So, and the cladding, the new cladding that goes on, is connected at very discrete points. So unlike a lot of other glass and metal wall systems, it doesn't have the continuous thermal bridges through it, and you end up with something that's much closer to a true R12 to maybe R15 insulation in that wall area. Another example building is the one labeled TP, which refers to the photo right above that. I was anticipating using a pointer, but that doesn't really work here. In the building photograph, that sort of goldy-looking modeled appearance one is the previous version of that building. The modeled version was redefined, redone, I guess, into the newer version on the right. There's an article I read a short while ago saying that the greenest building, the way to get the greenest building is actually not to build the building. Start with an existing building and then upgrade it. So what's done here is you're taking an older, not well-performing building, maybe 30 years into its life, and you're changing out elements that are readily changed, such as the glass and the spandrel covering. You increase the performance in the vision area, you change the materials so you get greater durability and so on. In an absolute sense, it's still not a very high-performing envelope, as John has pointed out, but in a relative sense, it's a significant improvement over what existed before. Another example building of people have been pointing to of something we should not do is the building in the lower left corner called Absolute, or the Monroe Towers in Mississauga. Been criticized in one way is that you're making the appearance of the building through the use of continuous balconies that wrap around the entire structure. There's about 4 of these towers being built, some finished already, and the criticism is focused a lot on the use of continuous balconies. If one actually took the time to delve a little bit deeper into this building, you'd find that the balconies actually incorporate a fairly simple but unique thermal break system all the way around the balcony slab. So what you end up with is the heat flow through this area is about 40% of the area of the typical balcony. So while it still has balconies and they're still energy net consumers, it's far less dramatic than it looks like when you look at the building as a whole. You also see buildings such as the one in the middle, which is actually, a rendering, but where you've taken what many would look at as a window wall system, and you've actually made a hybrid system using something closer to curtain wall. So again, in absolute terms, not a high-performance building, but in relative terms to other window wall structures, considerably better. So in terms of, we've talked about throwaway buildings. The two terms that come out most frequently is the durability of the building and its energy or energy consumption or performance. Case in point with the first Canadian place, the removal of the stone, durability is not an inherent property of a material. It's a property of a combination of the material, its use, and the environment that it's used in. The white Carrara marble, there are examples, hundreds if not thousands of years old that we find in Europe, throughout Europe, of this material being used. But when you take that same material, move it to a cold climate, cut it into thin pieces and put it on a high-rise building, it becomes no longer a durable product. The focus of most current codes in Canada and other parts of the world is more on the performance right now, not long-term performance, not durable performance. There are references in the building code that say, more or less, thou shalt consider durability, but that's sort of very much of a motherhood statement. There are standards such as S478, which is referenced in LEED, which again are trying to develop and promote durability, but not in maybe a very thorough way. From an energy performance perspective, there are claims that the high-rise condominiums will now need to be analyzed using computer methods and so on. They have been analyzed using computer methods in terms of an overall building performance for the last 10 to 15 years. The approach that's generally taken is a system design method, where you have the entire building can consume X amount of energy, and you can distribute that energy consumption between different components. So you put in a high-performance mechanical system, allows you to put in a lower-performing envelope. Maybe the prescription needs to be changed in that regard, but they are complying, they are meeting what is the current policy, if you will. If we look at performance standards, again, as was already mentioned, there's a tendency to apply performance standards differently whether you're building a commercial building or whether you're building a residential building. We're looking at the same things, such as air leakage, water penetration control, obviously structural performance. The buildings have to stand up. The thermal performance of the envelopes, other things like fire resistance and acoustics and so on. But nearly all of these tests, all of these performance tests are at a point in time. You take a sample of the wall, you test it in a lab once to determine its air leakage level. You test it once to determine its water penetration resistance. We're not looking at performance and how that will even perform a week later, let alone 20 or 30 years later. There are recommendations in the industry that say if you have your lab test, if you're going to test it in the field, you should only test it to 2/3 of the performance level, because there's an expectation is that when you actually build it, it won't perform as well as it did in the laboratory setting. There's something fundamentally wrong with that approach, because you're already accepting that performance is degrading, and that's only within a month of the original design. When we're looking at residential high-rise buildings in particular, up to very recently, most designers were relying on standards that were developed around a small residential window. So you're building a 40 or 50-story building completely wrapped with what is essentially a window product, but you're basing its performance on something that was really meant to go in a fixed opening on a low-rise building. In terms of thermal performance, particularly, we're using the same materials, whether we're using a commercial building or a high-rise residential building, but we're putting them together in different ways, and the way we put them together drastically impacts the way it performs. The example on the left would perform markedly better than the example on the right. Again, due to the density of the framing, the frame effects generally conduct more heat flow, you get less overall performance. The tools that we need in order to evaluate aspects of thermal performance have existed for a long time. I remember doing two-dimensional thermal simulations a while ago. I'm not.
Don't age yourself.
I mean, I'll stop there. But quite a while ago, and even today, we come up with thermal modeling, and we still get people, in disbelief, saying, "Well, that's not possible. We've been doing it that way for years, and it performs way better than that." If you look at these two sections cut through on the left, a commercial curtain wall, and on the right, a window wall product, a quick look by a lot of people at the image on the left, to scale, it's maybe about 8 inches. The overall section is about 8 inches deep. You have 4 to 5 inches of insulation in that section. That seems more than adequate. That alone, say it's 4 inches, would give you about R16 across that section. But when you take in the three-dimensional problem, you take in the vertical framing, that R16, or the R16 quickly goes down to the R5, R6 level. I was in an architect's office not a couple of weeks ago, and they were adamantly maintaining that every building they'd designed had at least R12 to R16 in these spandrel areas. This is 2011, guys. We knew this a long time ago. On the right is a section through a window wall slab edge condition, where right at the slab edge, the actual R value, if you will range from about R1, which is fairly typical. It's very easy to boost that to the order of R4, R5, and requires about a 15-millimeter shift in some framing materials. But even that sort of change encounters a lot of resistance because it's not the typical thing that is done. It's sort of my closing 2 slides, so hopefully I'm not too far behind. Sort of a famous quote, "Form ever follows function," by Louis Sullivan, who's sort of considered the father of the high-rise building. It typically gets shortened to "form follows function." And a lot of aspects of building design, that is true. If we look at at a really classic example of form following function. You think of the the stealth bomber, the black sort of flying wedge of cheese. It's really designed around the first thing you have to do is make it undetectable to radar, and that defines the shape of it. You add in a few other things so it can fly, so it can carry payload and go a certain distance. But you've got the form of the assembly follows the function. When we're designing buildings, the form in the sense of its structural form is meeting certain things, the way the foundations go and so on. But when we come to the building envelope, I would argue that in a lot of cases the function's following the form. We recently had sort of a challenge from an architect client. They'd said they sort of felt they'd come to a wall, so to speak, in terms of the performance of the exterior of their building envelopes. And what could we do further? What ideas did I have that could improve the performance? So I went through the sort of the normal things that you could do related to materials, insulations, thermal breaks, positioning of different components, how you could assemble things, and that all just gives you an incremental increase in performance. But then I sort of came to the conclusion in the meeting that that's part of the issue, but another part of the issue is the whole process that we go through in designing this aspect of the building. In the normal process, it starts with a developer who has some money, wants to build a building. He contracts with an architect and maybe at the same time with his exterior wall supplier. Between the three of them, various different parties holding sway, they come up with what the exterior of the building will look like. Then the rest of the team comes in terms of the mechanical engineer, electrical engineer, exterior designers, my role in terms of the design of the facade. And our task is to make that building now work. So we're sort of given a lot of constraints, and we're trying to make it the best we can. So what we end up with is a compliance. We have to get code compliance first of that assembly. And then beyond that, we're trying to still make the rest of that work as best we can. One way to resolve this would be alter the process completely. Is you have the developer, and either through a policy directive or the developer engages the facade designers earlier in the process who sets a series of rules. And then you bring in the creativity of the architect to apply these rules to your building, and you actually change the shape and form of the building, but you end up with a better performing product. When I laid out that process to the architect, they very quickly lost interest. But what it points to is that there are constraints in the hands of the architect and some on the developer, some on the contractor when they start, and those constraints then get enlarged and passed on to the rest of the design team, and there's a lack of ability to design the best building envelopes. We're basically trying to design the best given the constraints that are provided to us. And the role that policy may have is either coming in the process before the developer sets his goals on something, or between the developer and the rest of the team in the design process.
Thank you. We have time for questions for a while. I just wanted to start off with one. The pyramids are about 5,000 years old, I think. We have, I know there's cathedrals in Europe that are 1,000 years old, and there's probably some palaces and other buildings that have been occupied for about 1,000 years. And I just wonder, how long is a building supposed to last? We talk about throwaway buildings, but engineers design plenty of things that eventually aren't useful anymore. They come to the end of their life. You might not call it planned obsolescence, but things obviously age and are no longer worth keeping. So I just wonder, how long should a building last?
Well, first of all, the Egyptians had the advantage of living in a desert and having slave labor. Yeah. So the pyramids is just completely not. I understand why you use these. Yeah. Similarly with cathedrals, I mean, these are not comparable to our building process. Yeah. However, the comparison I think that matters to high-rise condos is that the buying public has a cultural expectation of purchasing a home and actually selling that as an asset as part of their retirement or passing it on their family. So that's got nothing to do with technology. That's got to do with what people's expectations are. And so I don't have an answer for what year, how many years it should be, but but clearly it should be something that is in the order of what the consuming public assumes they're getting when they put down their money. And there has been a good trend towards institutional investors who are not homeowners figuring this out and hiring Mark or hiring me to make their building skins better because they were unhappy with what they had. So 25, 30 years and then major renewals, that's not what they wanted. So we're going to find out what that answer is, but it isn't 20 to 30 years between major renewals. We'd like to stretch it longer. I'm more worried as a public policy issue of protecting consumers who think that buying a condo downtown, a city place, is the same as buying a house built that their parents had, that they purchased in 1950 and is still relatively solid with relatively modest injections of maintenance and renewal for windows and roofs and all that. So I think it's just a matter of, if we told people that your condo is going to appreciate at a lower rate than at your parents' home because you have to put more money into your reserve fund, and that at the end of that process, you might actually have to put even more money in, that'd be fair, informed consent. But I think that that's the concern I have from a public policy point of view, is there's confusion between what they think they're getting and what they're getting.
Okay. Can I comment? I guess two things. One is age is interesting in a city that's as young as Toronto, but anyway, I have friends in Edinburgh who live in a house in multiple housing that is well over 300 years old and has had different lives over time, but basically is joint ownership and is maintained, and there's a system in Britain that allows that to happen. The example I showed, one of the examples I showed you of very early Page+Steele work is 70 years old. It's a successful apartment building that's been maintained, and I would expect it to last a considerable amount of time. Glenn Gould lived in it for 30 years before he died, for example. But and then I live myself in a house that is 120 years old, and I disagree a little bit with John in terms of the costs of maintaining a house. You know, I've lived there for 35 years. I've spent considerably more than the original cost of the house, probably twice as the cost of the house over that time, replacing all the glass, insulating the building, replacing the kitchen once, and a number of other things, which you can imagine happening in any kind of residential process. Mm-hmm. So I think there's the big deal that I see in condominium work, and I probably worked on one of the very first projects in the 70s, in the early 70s when the Condominium Act was issued, is that the joint ownership and the understanding of joint ownership, the understanding and maintenance of reserve funds is such a huge thing to make sure that the buildings can be renewed with time and I'm not sure that legal structure is really in place to make it happen properly in Ontario. Mm-hmm. Mm-hmm. Any other questions? All right. Sure.
I think this might be a question for Tim. Vancouver is a serious earthquake zone. How advisable is it to put up high-rise buildings with large amounts of glass on the exterior?
Well, I'm trusting to people like Mark and the structural engineers that their solutions do work. The earthquake requirements for Toronto have actually been enhanced in the last few years, and there's more work being done on the stability of the buildings themselves and so on. But I really think it is a structural issue. I mean, there's still, I don't believe you'll ever have a building that's going to have less than 30-40% typically. You can imagine as I said, the smaller units might only have an exterior exposure of 20 feet of width, mm-hmm. and that's for a living room and a bedroom and other functions. So to have 20 feet is 160 square feet, and if you reduce that down to 40%, you're only talking about 40 square feet of glass for 2, possibly 3 people living in an accommodation, as against a small house which would have significantly more glass, more viewpoints. So it's very hard to see a significant reduction of the amount of glass. I don't know, Mark, in terms of the stability, do you have an issue?
Yeah, well, it's a very good question. If you look at any world cities that have had major earthquakes in the downtown core, you more or less see almost a foot depth of falling glass, because glass that have broken on buildings. If we go to places like San Francisco, Los Angeles, or Japan, where over the last, let's say, 20 or 30 years, I mean, people have been very conscious of that aspect of design. There are buildings that go through the earthquakes that don't even crack a pane of glass. So, we can design to certain levels of earthquakes. We do routinely now do testing where we shift the floor slabs to mimic movements during earthquakes. In the Toronto area, we're in a very low seismic design. Our criteria for shifting might be in the order of 12 to 15 millimeters, which is pretty negligible and very easy to do. So in Toronto, we don't probably have a great risk. In Vancouver, we're routinely testing for up to 3 inches of movement, floor to floor. And we can design most areas of the wall to work fine. Sort of a little caveat there, because problems always happen at building corners and so on, where things move a little bit differently. And the testing parameter basically is that nothing falls off the building. Things may break up to that level of movement, but nothing falls off. I can see as we go forward, as I say, places like Los Angeles or San Francisco, a lot of the glass is laminated glass. So if it does break, it can be retained in the opening, which is sort of the design thrust that we're going towards with the balcony railing systems, is that it become laminated rather than fully tempered glass.
2 days ago, I was in Norfolk, Virginia, in a top secret briefing room for the Navy facilities people. Nothing top secret. It just put us in a room that I couldn't use my BlackBerry. Anyway, they are actually designing buildings to take explosive charges depending on, there's 3 different threat levels. I can have a pickup truck with 4,000 pounds of TNT sitting 60 feet away from a picture window, and we can structurally design that. All it takes is money and engineering. That's the good news about the structural side. It's still not a precise science, but it's pretty close, and we can predict these things. So all we need is for someone to pay attention to things like earthquakes, blast, people falling against the window, and we can design, because those are really, we identify the load, right? There's a good process in there. We have no such process in most building science things. We have no process for assessing durability like we do for structural loads. And that's why they're very different type of things, and I would trust Mark designing a building in Vancouver for earthquakes, because we got good policies and standards and education in place to handle it.
Yeah, Len King, Western Regional Councillor. Before I retired, I was the chief building official for the city of Hamilton, and it was experience with dealing with the building code as far as new products and new materials that, as an engineer and as a building official, I would look at it and think, I can't see how that would be reliable or would have a long life expectancy. But as a building official, the only power you have is the building code, and if the building code doesn't specifically require something, then you can't ask for it. I think the broken windows are just a symptom of many other problems. In Hamilton, we had 2 buildings that 22, 24 stories high, solid, well, it was brick and concrete block composite wall, and it was built in the 60s, and it failed. The brick came off from about the 3rd or 4th story up to the 18th story in one big panel, so 60 feet by 200 feet of brick came off all in one event. And when it was investigated, it was found that was the state of the art as far as knowledge back in the 60s. And that building it was the east side of the building, so a nice spring day and summer sun hit that wall, and it was brick ties rather than metal ties. And those brick ties have been breaking off one by one over the years, and it finally got to the point where it failed. Subsequently, the building right next door, which was also owned by the same people, built around the same period of time with different architects and different contractors, it failed as well. So there's probably other problems out there that are going to come forward. And I think the building code, one of the main things, is the building code should address the life expectancy. Just one example, the building code in Ontario requires that lintels be made of, where they're made of steel, should be primed, which is, that rust, red rust paint. and half the time they're only partially primed. It's a very sloppy process. For example, in the UK, those lintels have to be hot dip galvanized and painted epoxy coated as well in addition to that. So our lintels probably last a couple hundred years. Theirs will probably last 1,000 years.
Well, it's commonly said, I guess, particularly in the market-driven industry, that the building code is both the minimum and the maximum for everything that is done. And if you go to a condominium that perhaps is in the mid-market, any client will expect that building to be built at the minimum and the maximum, and has to satisfy code. And right now, that in Toronto market may mean a cost of about $200 a square foot of construction. It's extraordinarily difficult to make that, to push that up, to change that, to encourage the clients to spend more money for whatever purposes. If you look at leads, for example, which is not necessarily the best route to take in some cases because it involves a lot more things than energy that aren't necessarily a part of a good building. The only one, except for one client, the only one that we've been involved with, all of them except for one client, were generated by a requirement by the city to provide a lead building if they wanted more density. Right. There had to be a financial return to the client in order to make it happen. So the combination of market, I was joking with Mark that is form follows function, should really say form follows marketing, is that everything you see practically is being generated by what the client and his marketing people say can be sold. They're generally having very big success right now, and they're hard to argue with. So it is a problem.
But the code is, as you mentioned, the code is the worst possible building you can build without going to jail. And it's also, ironically, a four-letter word. So, but the thing is that developers will build, will market what they can build, et cetera. But you know what? They still somehow find the money to put in 2 emergency exits on every floor. They still somehow find the money to put in standpipe systems for fire department. So all of this, whatever standard you want to look at, has been driven by what is a societal need. So the market will do whatever the rules tell us. It is not the other way around. Society should be saying, how safe do our buildings have to be? It shouldn't be, well, the market will afford this, and so we're going to do it. And that's why I think this is an appropriate discussion at this type of conference, is that, well, wait a second, let's not give up as a profession, either architecture or engineering, saying, well, you know, that Minto says we have to build that. Even though Minto actually does good stuff. But I mean, don't kick rock. I'm just using them as an example.
They're the one that does lead buildings without being told.
Right. They actually do good stuff. I'm just pointing out that it's not at all the intention of public policy or the average person to say that you should be building it as cheap as possible. That's the reason the code is to make it no lower than that. And like primed lintels are a perfect example. That is just screwing the public, because it's offloading what is a clearly predictable durability problem onto a future owner. And that's why we need lemon laws. That's what the building code should be trying to do. And I think the developer then should build to that. And they don't need to exceed that, but they should at least allow society to decide if it's $210 a square foot to get a much better building, well, then that's what society has to decide. And it doesn't have to be a lot more than that $10 a square foot premium to make a really big difference.
An obvious example in Ontario is the sprinkler law. That, in spite of what we were telling clients for the last 20 years, we haven't been sprinkling apartment buildings, I guess, was the exemption. In spite of the fact that every single jurisdiction in North America has had that as a requirement of high-rise apartment buildings, until 2 years ago, apartment buildings weren't sprinklered in Ontario.
Yeah, just one other comment, Bernie.
Sorry? Oh,
with respect
sorry.
to your pyramids not collapsing.
Yeah.
Of that era, Hammurabi's building code was that if the building collapsed and killed the owner, the builder shall be put to death.
Yeah, that's right.
It was fairly effective.
Yes.
You think liability?
Over here.
John, Tim, Mark, thank you very much for your interesting presentations and your points of view. My comments are kind of multi-pronged. So with regard to Tim's comments with regard to single-family residence, and you'd made the comment that approximately 20% of the outer facade of anybody's residential residence, single-family residence, is 20% or window glass. My question is, what would be the aggregate R value of the window glass with the wall and whatnot to make up that house? And then my question goes back to high-density housing. Do we meet that same minimum R value for that high-density housing? And then to Mark's comment about form following function, I think it's an excellent point that function is following form. So if we pushed it back the other way and said, okay, we have to have a minimum R value standard that each one of these walls must meet, would we then get better energy usage? And the reason I ask that, I'm an engineer here at Toronto Hydro, and so I'm very interested and very concerned about energy usage. So when you have homes that are, or high-density housing that's essentially all glass, it's all greenhouse, well, that pushes up our load, that affects our system. That affects everybody in the province. Everybody's paying for it, not just Toronto Hydro customers. Everybody pays for that. So my question is, if we have minimum R standards for these high-density housing, this benefits everybody. It becomes a larger societal good. Has anybody looked at?
Well, I think there's, I believe if you listen to Mary Weems' week of reports, one of the issues that was mentioned there is one that I think is quite good, is that builders should be required to give the energy performances of their units, of their buildings for sale. Certainly, I bought a condominium for my daughter very recently, and I was very concerned about that aspect of it. And probably I didn't buy one of our own buildings, but for her particular use, I chose a building that had less glass, no balconies. Her share of the cost is significantly less. Her actual operating cost is less because of a greater amount of insulated exterior wall, I guess. But it would have been so much easier when we were looking at all these various condos to see how they compared one to the other. The same as if I buy a refrigerator.
Yeah, but a fridge is like $600, so we have a lot of regulations in place.
Of course, yeah.
I have one more question with regards to that. Do you think one of the reasons we don't have a drive towards more energy efficiency is because we have non-resident owners, people that are buying from offshore and don't actually live here? Do you think that might be a driver or no?
Well, I don't personally think so, because I think the costs of operating the buildings are typically dumped onto the residents in any case. So, when people rent units, as far as I understand, the smart renter anyway is asking those questions. Well, what is my monthly cost? What is my expected utility cost? I certainly did it, as I said, with my daughter's unit.
Thank you.
Okay. I just have one more question. It's not really a question aimed at the panel. I'm kind of throwing it out to the floor just for consideration. We heard a lot about the role of marketing and developers. They turn over the building fairly soon afterwards to other people who aren't involved in the discussions about what the building's going to be built like. But on the other hand, the engineers involved in the project have a duty to the public, to the wider public. And I just wonder whether engineers need to be seen more as advocates for that public, for those eventual owners, standing up for their rights in pushing through the designs with the clients that the engineers think are more appropriate. I don't want to ask you guys if you've ever acted as advocates for owners, so I'm not expecting an answer there. I'm just sort of putting it out there as a question for everybody to think about. I'm very pleased with that. That was a very interesting conversation we've had on this subject. I hope we have more of them like that. on this subject and others. I do want to thank our panelists, John, Tim, and Mark, and we have some gifts. And now we can go to lunch.